I'm Kristi Belcher. I'm from Lawrence, Livermore. We're here to talk about UmpireSpace, the Kokkos MemorySpace you've always wanted. This was a work done with myself and David Beckinsale. Okay, so to kind of jump things off here. Umpire is an open source C++ library. It does have a Fortran interface, which is very exciting for some people. And then it was developed at Lawrence Livermore. But really, Umpire abstracts away the vendor-specific details and then provides this unified portable memory management API to accommodate modern HPC platforms. And I really want to drive the point that it allows developers to efficiently utilize heterogeneous memory resources while remaining portable. Another kind of important point here is, it provides support for querying the memory resources, and then provisioning and allocating that memory, and then a little bit of memory introspection, so you could kind of query things about your allocators. So it has these key features, and we'll see this throughout some code examples, but there's the memory resources, which kind of represent the different types of memory available on your system. So, device memory, host memory. You have your allocators, which is what you primarily interface with when you're doing your Umpire allocations. And then some cool allocation strategies. So there are kind of more sophisticated memory allocation algorithms, stuff like memory pools, which are very exciting. And then we have our operations, so you can do like a copy or a move through Umpire. Okay, so just a very quick little code example. So the top one, okay, you'll notice in both of these sections, really, the first thing we do is we get this resource manager, okay, and then you will use that resource manager throughout all of your code. But so in the first upper portion here, we are using the resource manager to make an allocator, and then we're going to use the quick pool allocation strategy, and we're going to give it the underlying memory resource of device, okay? And then you can build upon that with a thread-safe allocator strategy, and you build upon that with the pool you just made, so you're building upon it to make a thread-safe quick pool that uses the device, a memory resource. And then you do your allocations, you do your calculations, and then you deallocate. Okay, and then the one on the bottom there, very similar, except I'm just highlighting that we can use the resource manager to do a copy from from destination, from source to destination. Cool. All right, so a little bit more on memory pools, which is the most exciting part of Umpire. In fact, Christian's favorite part of Umpire is memory pools. So this allows developers to pre-allocate all the needed memory at once instead of making multiple smaller memory allocations. So the memory pools really try to address the limited memory resources on HPC devices, and it tries to make device allocations easier as well. But so I have this little graphic that tries to show, you have your underlying allocator, and then there's these chunks of memory that you can allocate. In that little blue box, the memory pool is essentially one large allocation made up of smaller chunks of memory, and then, as a user, you can query that, you can allocate and deallocate memory from that pool. But importantly, okay, the pool is not a contiguous chunk, but dynamically sized multiple chunks. And then, as you allocate and deallocate, that pool will grow and shrink. It's shown great success. We have had some Kokkos users express interest in exploring performance benefits with those memory pools. So I have this cool little benchmark, and it just shows a very simple comparison of the quick pool versus native HIP calls. And it shows that quick pool is, okay, over 15 times more performant than native calls, but that's really just because the large chunk of memory is pre-allocated. So now you avoid that overhead when you're actually doing the allocate, deallocate. So it's so much smaller because we're not actually doing any memory allocation behind the scenes. We're just moving pointers around in the Umpire quick pool. So, yeah. Okay, so like I kind of alluded to before, Umpire provides more than just the memory pools. So we have a very cool support for IPC, or inter-process communication, and MPI3, shared memory. And then, like I mentioned a little bit before, we have the thread-safe allocations, the composable features. I keep using the example of a thread-safe quick pool, but there's many different combinations you can make. That's just an easy one for me to call on as an example, but we have many composable features. And then, of course, memory introspection, which kind of gives you more information about your allocations. And then another cool, important thing to note, okay, is that Umpire works with these large integrated codes at the lab. So we know that sharing the allocators between the application parts works really well. So one cool example I know is that you have a large simulation, and then you have your separate visualization component. Well, now the simulation can share an allocator with the visualization component, and we've seen that the visualization will have more memory doing that than it would otherwise have. Specifically in situ visualization. I just want to put that out there. Okay, so that's been very successful at the lab. Okay, I have to caveat this way before I. So I am by no means a Kokkos, MemorySpace expert, okay? But I want to just make sure we're all on the same page with some context, okay? So I just want to kind of put the definition of a memory space out there. It's an abstraction that represents a distinct region of memory on a given hardware device. I think that's kind of intuitive. So it really tells Kokkos where the data lives, and then there's different options you can have, and that's not an exhaustive list or anything, but that's some of the major ones that I saw. Yeah, so they're primarily used when declaring Kokkos view, and then they determines what execution spaces can directly access that memory. So if you have CUDA space, then you should be having a CUDA kernel. So, and then again some code examples there that's just kind of prepping us for the cooler memory, or the cooler code example that I have later on. Okay, cool. So adding Umpire to your Kokkos implementation could help overall memory performance, and we really want you guys to try this out for yourselves. We're looking for people to use the code that we have developed to make Umpire and Kokkos work together. But it's important to note that Umpire is built to be modular. You can use Umpire with Kokkos, or you could just use Umpire by itself, if you have your own abstraction layer. So it can be used with Kokkos, and the memory pools have really demonstrated good performance gains on the HPC applications that we've seen. And we have users both at Livermore, in the labs, and then beyond, and external users. Okay, so there was growing demand to use Umpire and Kokkos together. So we created a collaboration with the Kokkos team to create UmpireSpace. So because Umpire and Kokkos were becoming friends, I thought this meme was perfect. So if you've never seen Step Brothers, I highly recommend that you watch it. But yeah, we are essentially best friends. Okay, so code example, the coolest part of this talk. Okay, so the way that I have done this is it's all color-coded. So the green is the additional code you would need to add to have UmpireSpace happening. And then we have the blue for code that is well known for any user of Umpire. And then we have this like orangey reddish color for code that is well known for anyone who is a Kokkos user. So if it's green, it's new. And of course, this is very simplified, so it's kind of a hello world UmpireSpace example. So the first thing you do is you create these host and pool tag types to use the backend Kokkos MemorySpace. And I have a little bit more about this on the next slide. So yeah. And then you set up your UmpireSpace allocator types and views. So we're going to make a pool space type with, we're creating an UmpireSpace. We're using the Kokkos hipspace backend. And then we're using that tag type that we just created above. And then we're going to define this view type, okay, which is just making a Kokkos view. It's going to be doubles. And then we're going to pass in that pool space type that we just created. And then we're going to do something extremely similar for like a host space type. So we're going to use the host tag type that we created above, the Kokkos host space, and then, of course, doubles. Okay, so then we initialize our favorite thing to do in Kokkos. And then we're going to have our Umpire code there in the blue. Like always, the first step is to create the resource manager instance. And then we're going to create an allocator. So we're going to use the resource manager to make an allocator, which is going to be a quick pool. And we're going to give it that memory resource of device and then an initial size. Okay, so we got all this set up. And then the next step is more code specific to UmpireSpace. So we're going to use the allocator names that we created above to initialize the UmpireSpace for both pool and host allocators. So that pool space type, you're going to set it to an allocator of the pool you just made. But then for the host space type, you're setting it to the host memory resource, like built-in allocator from Umpire. Okay, and then the second half. Okay, so now this is all easy, right? Because this is just Kokkos code, whatever. So you create your views. You're going to use them in parallel fours. You're going to do something super simple. You're going to synchronize, and then you're going to deep copy everything back to the host so that you can print it out and check it. And then you finalize. Your second favorite thing to do with Kokkos. Okay, so this is very simple, but we can, it's like a proof of concept that these things work together. It's a hello world, just kind of warming us up to doing this stuff. But it's important to note that the additional code needed for UmpireSpace is somewhat minimal, and then it'll get more minimal as we make this kind of improved UmpireSpace. Because right now there's like little tweaks you gotta make here and there, and so after some time we'll kind of massage that and get all the kinks worked out. But essentially this is all you have to do. So very exciting. And then a closer look here. Okay, so I mentioned the tag types before. That was the first thing you ever did when you were doing the UmpireSpace. This just allows you to create multiple allocators or multiple memory pools that both use Kokkos's hipspace backend. Kokkos kind of frowns upon that, but in this particular circumstance, it makes a lot of sense. A lot of code developers want two different memory pools, one for like temporary allocations, and then a separate pool for permanent allocations. And so if you want to get that set up, then the tag types really help you, because you would just have like pool 1, pool 2, and then that helps make everything work. And then I just want to like call attention to a few ways that Umpire is different than Kokkos. So you may have noticed that Umpire is dynamic and runtime based. And then we have this central resource manager, which is a singleton. That's kind of different from the way that Kokkos does things. And then Umpire also explicitly discovers and registers memory resources available on the platform at build or configure time. So you're using the device memory resource, but whether that maps to a hip malloc or a CUDA malloc is going to depend on how you built it. So yeah, it's also kind of different than the way Kokkos kind of works. And then the allocator behavior is meant to be composed. So this goes back to our thread-safe quick pool that uses the device memory resource, right? You're using the memory resource, you're building allocation strategies on top of it. But that's not going to change the underlying allocator interface. Okay, so UmpireSpace, you can use the Umpire Memory Management API with Kokkos. And then developers will have access to all of Umpire's super cool capabilities. Very exciting. And right now, UmpireSpace supports HIP and CUDA, and then host backends. We've done more testing with the HIP backend just because of the machines that we have at the lab, but the CUDA side should work too. And then some future work. Okay, so currently UmpireSpace is in a separate GitHub repo. We plan to make this part of the Umpire repo, and it's just a header file. So if you can point to that header file, then you should be able to seamlessly use Umpire and Kokkos together, and it should be great. Yeah, so we're Umpire and Kokkos teams are kind of working together to figure out how exactly we're going to distribute this UmpireSpace. That's our plan so far, but definitely tell us what you think. And my favorite part, UmpireSpace has some really cool documentation and an example and some like step-by-step instructions on how to build everything together, because like I said, right now it's in a separate repo, so it's kind of not optimal for trying to build into Umpire and Kokkos, but I have some really good step-by-step instructions. Okay, and you can you can test me on that. Just how good is it? So that QR code, as of last night, totally worked. So I'm hoping it still does. That'll bring you to the Umpire Kokkos GitHub, where we have all of this code hosted. Like I said, README, a quick start guide, very good. We have our Umpire's email address if you have questions or things don't work. So yeah, just kind of let us know how it goes. And with that, the end. I'll finish.
Thank you. Any questions?
In your example, how did you associate the I guess the resource manager with the actual like memory pool you set? Because you kind of declared things before and then you made, but I couldn't really tell where you generated your resource manager and then somehow that got associated to the actual UmpireSpace types, and I didn't really see where that step was.
So in the first, green chunk of code right at the top, that's where you're using things that have been defined in this header and setting things up. As long as you've created those pool types and you're setting things up with the UmpireSpace, then it'll just kind of connect itself. Yeah, I mean, That's, yeah, it's just things that have been defined in the header. Yeah, oh, yes, okay, sorry. Yeah, okay, cool. Get it out of there, okay.
I didn't see like a free or like a release of something that came from the pool. So are you using Kokkos's reference count to determine when something can be released back to the pool as available?
So there is a reference counter, but like once you set up that allocator, it's relying on Umpire's way of, you know, giving, like allocating memory, giving it back. So once you
It's like when the view, you know, is going to go out of scope or is going to run out of, you know, it's going to collect the allocator. And then, you know, if you have hierarchies, then if hierarchy is like, oh, the allocating means something slightly different than you're usually used to, which is eventually returning them to the pool. So like, it happens under the scene, under the scene.
But it's all hidden.
Yeah.
Okay.
Yeah. There's, I feel like, do we have time for questions? Because I'll be at the breaks too, so.
Maybe one more?
Okay, yeah.
So maybe this is trivial, but if you have to have the resource manager as kind of something that's shared across translation units, does this imply that you would need relocatable device code on the GPU side to use this Umpire thing?
No, no. Yeah, there's only like a few features within Umpire that actually require relocatable device code, but unless you're using those two very specific things, then no. Yeah.
No, not in the integration with Kokkos, because there's nothing that happens in kernels. It's just allocation, deallocation.
Okay, yeah.
Thank you.
Yeah, do you have